Okay, for our third speaker, we are pleased to have Sambit Panda. He's a PhD student from Johns Hopkins University, and that is also where he got his master's in biomedical engineering. And before that, he was an undergraduate at the North Carolina State University and the University of North Carolina at Chapel Hill. Today, he will tell us actually about his new work on decision forests, where he has developed methods that actually have higher testing capabilities compared to existing methods.
Hi, my name is Sambit Panda, and I'd like to thank the Global Young Scientist Symposium for allowing me to talk today about a paper I wrote called Nonparametric MANOVA via independence testing. So the real motivation behind this talk was to really understand, this paper was to understand the relationship between K groups. So control versus disease patient is a real common population, is a real common test. So we'd like to ask, are these groups related? And is a more difficult problem into, but are they related is definitely an important issue to think about. A little bit of background about statistics. Basically, we X to be some kind of random variable, which is some measurement. And then we're considering fx as the distribution of x. So basically, we denote that x is sampled from some distribution fx. In terms of hypothesis testing, kind of an informal intro is basically that the null hypothesis is some conventional belief about the phenomena of interest, and we denote that as H naught. Hypothesis about the same phenomena is HA. When we test, we try to reject the null hypothesis. And then U is a measure of confidence of our results that we get from our test. And so under a called alpha, we will reject the p-value, and that's in turn essentially rejecting the null hypothesis. Probability of observing a measurement more extreme than a given observation. So intuition behind our basically when we want a testing procedure, we want one that works well in low and high dimensional data. Especially important now because a lot of data in science is very high dimensional. We'd like it to work on structured data like images and networks. And then we'd like it to work with linear and nonlinear relationships and be able to distinguish both. And then we'd like to have one that is very computationally efficient. So going back to our motivation in the beginning, we used this to answer a question whether the groups are related. So multivariate ANOVA or MANOVA is a really common standard of currently. And so at the top here shows basically how one of the test statistics is computed, but essentially data is derived, it has a couple of assumptions that it makes, one of which is that the data is multivariate Gaussian distribution, and that each group that you're testing has the same covariance matrix. And these are very strong assumptions, not very present in data that I'm sure many of you use. Um, so there has to be some better test out there that doesn't make these strong assumptions. So before I go into our talk a little bit, so basically when we're doing independence testing, we're given two random variables x and y, and they are independent if neither contains information about the other. So essentially, we're seeing if their joint distribution, if we can separate their joint distribution fxy into their marginal distributions, which is fx and fy. When we're testing, that's our null hypothesis, and our alternative hypothesis is that fxy are not independent. So one test that we've developed in our lab is called multi-scale graph correlation. Basically, it computes this decoy test statistic whose math is shown at the bottom here at various values, and then it finds a smoothed max of the as the test statistic. Then it uses test, which is a non-parametric way of finding the p-value. Great. So now we have all of this stuff. What can we do with it? So basically, what we're planning on doing is to reduce this case sample testing problem described before into the independence testing problem. Actually, how we do that is we basically concatenate our inputs into X. Our inputs are U1 to UK, and they're concatenated into X. And we created a label matrix called Y that basically one-hot encodes everything in X. And we can run any independence test that we want, magic included. So this is a great framework because we don't to the like the actual test that we're using. So it's great. Okay, so how does it work in practice? So before I introduce our simulations, there's some two terms. Power is basically the probability of rejecting the null hypothesis when the alternative is true. And relative power, in our case, is the power of a given approach minus a reference approach. And in this case, our reference is MANOVA for our figures. So first, we wanted to look at the optimal settings for which well. So we have three different Gaussians. So first, where all the means are the same. The second, where one of the means is different. And the third, where all three of the means are different from one another. And we see that our tests perform about as well as MANOVA does as we increase the separation of the clusters. Next, when we look at keeping the separation, increasing the dimensionality of our simulations, we see the real power of our test. We outperform MANOVA at high dimensions, so perform as well or better than MANOVA. And because of singular matrices issues with MANOVA, we are able to perform at higher dimensions indicated by the dotted line. Next, we wanted to look at not just Gaussians, but distributions that are used in the machine learning literature for tests. So we looked at each of these and we just took one sample and then rotated it twice to get two other samples. So here we show our relative power curves relative to MANOVA. So anything above 0 is better than MANOVA. Anything below 0 is worse than MANOVA. And we see as we increase sample size and fixed angle and dimension, we perform well in many cases. When we increase dimension instead, we see that for many we outperform MANOVA. We look at increasing the angle while fixing the sample size and dimension, and we see once again we perform better than MANOVA in many of the cases. Next, we can extend our work that we described before into performing multi-way and then multi-level tests. So multi-way tests are basically just using more than one treatment group. So instead of one hot encoding, we would have more ones basically in our label matrix. Kind of looks what it looks like. So on the left is the basic comparison between distance matrix and multi-way distance matrix. Then in B, we show a strong multi-way effect. So weak in the sense that the top Gaussian is equidistant from the other two Gaussians, but we distance between the other two Gaussians. And we see that our multi-way or performs worse at low multi-way effects, but about as good effects. And if we look at a strong multi-way effect and increase the dimension, we see that our algorithm outperforms. Then level tests. So basically, we're looking at block permutation. So it's a little difficult concept. So I thought I'd show an animation basically. So if we sample from these two balls, from these two boxes, where the left two values must come from the left box and the right two must. We get a valid sample using this, but if we were to just considering which boxes each came from, we would get an invalid test. That's what we show here. So the null basically is we're looking at 100 points sampled from Gaussian, and then we sampled 2 points from each of those Gaussians. And as you can see here, just normal decor is invalid in this case, while our multi-level decor is not. And then lastly, we looked showing a real data example of using our test in practice. And basically using our multi-level and multi-way tests, we were able to find that the third embedding in this case shows basically shown that there's several new tests that actually already existed using our framework that perform better than MANOVA, as well or better than MANOVA, that our multi-way tests can give it when there's a strong multi-way effect suspected, and then we show that we can also to use multi-level tests. So next steps, you can find this code in my Hippo package that I wrote. You can install tutorials are linked there, as well as the paper for this work, and at the bottom are links. And then I'd like to acknowledge all the co-authors on this paper as listed here. So, any questions?
Okay, thank you, Dr. Sambit Panda, for a lovely talk. Are there any questions from the floor? Okay, maybe I'll just ask a warm-up question first. So Sambit, you are based at the Biomedical Engineering Department. So what are some of the first applications of these computational tests that you've developed?
So we've analyzed our lab is in particular looks at MRI, particularly structural MRI, and so we've taken subjects. I think I might have mentioned it briefly in the talk, but we analyzed um, patient meditators, expert meditators, and novice meditators, and they had different states, and we performed a multi-level test to see if we could find a low-dimensional representation of the MRI that offers some difference between expert and novice meditators. So that was one direct application we did. But honestly, we do a lot of connectomics research. So particularly taking a MRI, converting it into a graph, and then performing graph statistics is basically the main avenues that we've been looking. But I think this work can apply to many other fields. Just haven't
I see.
explored them yet.
Okay, so if you were to step out and have, sort of the one problem you wanted to solve with this test, what would it be?
Well, we're actually looking at a few new. We have a few new collaborations with some nonprofits. One in particular that I'm working with is Child Mind Institute, and we're trying to correlate brain states while watching a movie, and we're trying to correlate that with. And I think this test and some of the independence tests that we're also developing um, might help answer some of those questions
I see.
about
So
how
a
they're
lot of
related.
it is centered around MRI, is what it
A
sounds
lot
like.
of our work is really centered around imaging and neuroscience. So those are the things I'm passionate about. So those are the problems I'd like to work on. But I think like it can be applied to like genomics. I'm pretty sure also. So just any multimodal data really, or multidimensional data.
Okay, awesome. That's actually really, really exciting.
Thank you.
Okay, a follow-up question from me. So, what what do you think are the other problems that need to be solved to scale this up more widely? So I imagine you might have a whole deluge of many MRI images and things like that. Are there any other barriers to adopting this more widely?
Well, first, I guess knowledge of the tests. A lot of the independence tests that we're doing are new and need to be more, I think, widely adopted, since they are, um, while they are being used by some people in the machine learning community, when it comes to like some of the basic sciences like biology and chemistry. Um, I mean, I used to work in a lab doing chemistry, and um, we didn't do, I guess, like the most data analysis I guess we did was an ANOVA test, and I think that providing at least an alternative to that could be really beneficial, especially because ANOVA has a lot of issues when it comes to some of the assumptions that it makes. Um, I mean, in terms of, it's kind of really a little difficult question to answer because I think the applications I could come up with a lot of different ideas if I wanted to dream, I guess. But
Okay, but that's great.
uh,
Yeah.
it's a little difficult, I think, to come up with a few on the spot. But I think the application is very wide reaching.
Okay. Um, any questions from the floor? Okay, so maybe one last question from me. So instead of just throwing out different applications, going deeper into what you've done, what are some of your future plans to further develop what you've already worked on?
So yeah, so well, obviously my first plan is to publish this, and once I find the journal, I think our plans are basically applying this, extending this to paired K-sample tests. That's something we haven't been able to do with our framework yet. Um, Basically, we are also planning on, we're developing a new independence test based on random forest and mutual information, which could offer a more powerful test that operates really well on high dimensional data. And so I would probably try to take that test, obviously fitted within our framework, and see if we can get a really powerful finite sample K-sample test that operates really well on high dimensional data, and I think that would be really beneficial to the MRI community especially.
Okay, awesome. Well, thank
Yep.
you very much, Sambit, and let's thank
Yeah.
all of the
Thank you.
speakers and everyone for their participation in this session.